Just making the co-host. Can you make, yeah. Hi, Professor Witten. Can you hear me and see me? Hello. Can you
Hi.
hear me?
Yes.
Oh, okay, good, very good. So do we do a quick screen share test just to be on the safe side?
Okay. What are you seeing now?
Okay, perfect. I see the title. Yeah, it's perfect. It's good to go.
Oh, but I see a misprint. Or
Sorry, say that again?
no, never mind.
Okay. So how would you want to have the QA session? Should it be done via the chat? Folks write down the queries and I put them up to you towards the end.
Okay, that's fine. Yeah, we can
Okay.
try it that way.
Let's try that. Okay. Very good. So I think will it be okay if we start in about 3 to 4 minutes?
Sure.
Right. Okay, Professor Witten, should we start?
Okay.
Okay, very good. So, good evening, good morning, good afternoon, whichever part of the world we're logging in from today, right now. Welcome to the Mitra Memorial Lecture. This is a lecture to celebrate the life and the physics of Professor Ashok Nath Mitra, who could rightly be considered as one of the principal architects of the Indian high-energy physics community and the nuclear physics community. We are obviously so delighted to have Professor Edward Witten to deliver the Mitra Memorial Lecture today. And as is visible, he's going to talk about his work on background independent algebra and quantum gravity. So over to Professor Witten, please.
Well, thank you. And thank you for the invitation today. I hope you can you see my screen now?
Absolutely, yeah. It's all good.
Okay. Only trouble is I can't see it. Okay.
Do you want to unshare and reshare? Maybe that might help.
No, we'll be okay in a second. Okay. Now I can see it, and probably you can as well.
Yeah, we can see
So
it.
as you can see, my title is a background independent algebra in quantum gravity. So Let's start by reviewing the situation in ordinary quantum mechanics. In ordinary quantum mechanics, we usually consider the observer to be outside the system that's being observed. That's problematical in the presence of gravity, most obviously in the case of a closed universe. No one can look at a closed universe from outside. In ordinary quantum field theory, you have the freedom in what sort of operators we want to consider. And one important thing which we can do is to pick an arbitrary region U in spacetime and consider the algebra of all observables in the region U. So schematically, M is spacetime and U is a region. And in this case, I took it to be what's called a causal diamond. And we can consider the algebra of all observables in this region. In ordinary quantum field theory, we can pick any region at all in spacetime. There are some problems with this in the presence of gravity. First of all, since spacetime is fluctuating, we need to be able to explain what we mean by the region U. We can't describe an arbitrary region. There has to be some invariant way to define it. But perhaps more fundamentally, why do we want to define an algebra unless it's the algebra of observables available to someone who lives in the spacetime? So, So in the absence of gravity, we can imagine an observer outside the spacetime who probes the spacetime in an arbitrary fashion, but only in some chosen region U. So in the absence of gravity, we have the freedom to consider any region. But in the presence of gravity, first we need an invariant way to define the region. But more fundamentally, why are we trying to do this unless it's the algebra of observables available to someone in the spacetime? So I want to construct an algebra that describes measurements made by an observer. I'll assume the observer knows the laws of nature, but has no knowledge of the state of the universe, except whatever is observed. So this observer is trying to determine the state of the universe by observation. The second part fits our situation in the universe, but the first doesn't, because in the last few centuries, we've been using our observations to learn the laws of nature as well as learning the state of the universe. However, I make the first assumption because it would be much harder to model an observer who's trying to learn the laws of nature. So I'm only modeling the observer who's trying to learn the state of the universe. So I'll define an algebra that depends on the laws of nature, but it's required to be universal and background independent, meaning that it's defined once and for all with no knowledge of the specific spacetime in which the observer is living. Different spacetimes will correspond to different representations of the same algebra. Now, there's some relevant background papers on this, but I won't have time to explain all of them. I'll just say that the paper which is most relevant as background to my talk is this one. And what I'll be doing is rethinking the construction in that paper from a different point of view. Now, we can expect that in a full theory of quantum gravity, an observer cannot be introduced from outside, but must be described by the theory. For example, we ourselves are modeled by the standard model, which is the model that we use to describe particle physics. What it means to assume the presence of an observer is that we define an algebra that makes sense in a subspace of states in which an observer is present. We don't try to define an algebra that makes sense in all states. No one would be able to make use of such an algebra. First, let's describe the situation in the absence of gravity. The observer propagates into spacetime M on a geodesic that I'll call gamma. The world line is parametrized by proper time, tau. As in much earlier work, for example, by Unruh, the observer measures quantum fields along gamma. For example, the observer may measure a scalar field phi, or the electromagnetic field F mu, or the Riemann tensor R mu alpha beta, as well as their covariant derivatives in normal directions. Let's focus on a particular observable, say phi of x of tau for a scalar field phi, where x of tau is the observer's position at proper time tau. I'll abbreviate this just as phi of tau. When we take gravity to be dynamical, we have to consider that the same world line can be embedded in a given spacetime in different ways, differing by shifts of tau by a constant. So here's the world line. There's a well-defined difference in proper time difference between 2 points on the world line, but there's no natural zero of proper time. So we have to allow for the possibility of shifting the proper time by a constant. So 5 tau isn't by itself a meaningful observable. We need to introduce the observer's degree of freedom and define tau relative to the observer's clock. In a minimal model, we equip the observer with a Hamiltonian, which I'll call H observer, that's mc squared plus q. Mc squared is the observer's rest energy, and q is the clock Hamiltonian. And the variable canonically conjugate to q, I'll call p. However, it turns out that it's better to assume that the observer energy is bounded below, say by q non-negative, in which case m is indeed the observer's rest mass. We then only allow operators that preserve the condition that q is non-negative. So, for example, e to the ip, which does not preserve the condition for q to be non-negative, should be replaced by pi e to the I pi times pi, where pi is the projection operator onto q non-negative. So we freely write arbitrary operators that are functions of p and q, but before and after we project by pi onto states where q is non-negative. We now only want to allow operators that commute with the gravitational constraint. The important gravitational constraints, okay. When we do quantum gravity, the gravitational constraints enforce diffeomorphism invariance throughout spacetime. But along the observer world line, the only important diffeomorphism invariance is a shift by constant, because the action, or Hamiltonian describing the observer, fixes the coordinate system up to shifting by constant. So we first impose all diffeomorphism constraints away from the world line. Then we're left with one more constraint to impose. And that constraint is generated by a bulk operator that acts as a diffeomorphism in spacetime that shifts tau by a constant, as well as the observer Hamiltonian shifting the tau along the observer degree of freedom by a constant. So the final constraint, I'll call h hat, is a bulk operator plus the observer Hamiltonian. The bulk operator isn't uniquely determined, and generically there's no particularly nice choice. It's uniquely determined up to one of the constraints that acts away from the observer world line that we've already imposed. So what it means to impose this constraint is the following. An operator that we're only going to allow operators that commute with the constraint operator. Such an operator is invariant under a space-time diffeomorphism that moves the observer world line forward in time, together with the time translation of the observer system. Well, how do we find operators that commute with this last constraint, the crucial constraint that shifts the observer's proper time? Since the bulk operator commuted with 5 tau generates translations in tau, we need q commuted with 5 tau to be I phi dot of tau to cancel. Remember, q is the relevant part of the observer Hamiltonian. The observer Hamiltonian is a C number plus q. So q commuted with 5 tau must have this property. We can achieve that just by setting tau equal to p, or more generally, tau could be p plus a constant. So a typical allowed operator is phi as a function of p plus s, or more precisely, we should project before and after by pi the operator theta of q that projects onto non-negative q. So this is a typical allowed operator in the observer algebra. In addition to these operators, with phi possibly replaced by any local field along the world line, such as the electromagnetic field or the Riemann tensor, or their covariant derivatives in normal directions. There's one more obvious operator that commutes with h hat, namely q itself. So we define an observer algebra that's generated by all these operators phi hat s for all local operators along the world line, as well as q. Maybe I'll stop here and ask if there are any questions. Okay, well, if as I go on, if questions occur to you and you put them in the chat, we'll consider them the next time I stop. Now, the setup I've explained hopefully sounds background independent, since we described it without picking a background. But background independence really depends on interpreting the formulas properly. We won't get background independence if we interpret the symbols I've written, phi hat s and q, as Hilbert space operators. To get a Hilbert space in which they act, we need to pick a space-time in which the observer is propagating. Then we won't have background independence. To get background independence, we have to think of the observer algebra more abstractly as an operator product algebra rather than an algebra of Hilbert space operators. And then, if we think of it that way, the algebras for different spacetimes are inequivalent representations of the same underlying operator product algebra. In the absence of gravity, we characterize these objects 5 tau by universal short-distance singularities. For example, if phi behaves at short distances like a primary conformal field of dimension delta, then the leading singularity in the product 5 tau times 5 tau prime is what I've written, and then there's a subleading expansion in less negative powers of tau minus tau prime. That characterization did not require any knowledge about the quantum state or about the space-time in which the observer lives. After coupling to gravity and including the observer in the constraints, the short-distance expansion becomes an expansion in powers of 1 over q. We characterize the observer algebra purely by the universal short-distance or 1 over q expansion of operator products. With that understanding, the observer algebra is background independent. Now, there's a very special case of this that turns out to be important. That's the case that M is an empty de Sitter space with some positive value of the effective cosmological constant. So here what I've written what's called a Penrose diagram for de Sitter space. In a Penrose diagram, only 2 dimensions of space-time are depicted. One is the time which runs vertically in the picture, from time minus infinity at the bottom to time plus infinity at the top. Now, de Sitter space is a closed universe. A spatial section is a sphere. And our observer will be on a geodesic. An example of a geodesic is one that sits at rest at the South Pole for all times. So the left edge, I've chosen coordinates so that the left edge of the diagram is the South Pole of the sphere. The right edge is then the North Pole of the sphere. And from left to right, you can think of as being the latitude along the sphere. There are some angles. The angles along the sphere are suppressed. In drawing a Penrose diagram, one always assumes some spherical symmetry of spacetime, and one suppresses angles, and generally, the left to right direction in a Penrose diagram is some kind of distance variable, and up to down is some kind of time variable. And finally, a conformal mapping is chosen so that ingoing and outgoing light rays are at pi over 4 angles from the vertical. So the region that the observer can see in de Sitter space is bounded by this diagonal, the future horizon. Since signals will travel causally at an angle no bigger than pi over 4 from the vertical, anything beyond the future horizon cannot reach the observer. It will reach future infinity, the blue line at the top. So the past of this future horizon is the region that the observer can see, and similarly, the future of this past horizon is the region the observer can influence. So the green triangle, which really is a full space-time region, remember that angular variables are suppressed. The green triangle is the portion of spacetime that the observer can both see and influence. If you want to do, not, of course, you can look out in space through a telescope and see anything to the past of the future horizon. If you want to actively do an experiment, you send out, maybe you shine a laser beam on something and it is reflected back. Objects you can probe that way have to be inside this green diamond. You can influence them and you can also see the results. So the green diamond is the region causally accessible to the observer. It's called a static patch because it's invariant under a particular de Sitter generator H that advances the proper time of the observer. So in the de Sitter group, there's a generator H that maps the observer world line to itself, translating the observer's proper time forward in time by a constant, and not acting on the angular variables that are suppressed in the picture. So it's a symmetry of this picture, mapping the static patch to itself. So from the observer's point of view, the conjugate to this H can be thought of as time. You could think of it just as the proper time on the world line. And in that time coordinate, the static patch is time independent with H as its Hamiltonian. So the green region is therefore called a static patch. In the absence of gravity, there is a distinguished de Sitter invariant state, which I'll call psi ds. It's sometimes called the Bunch-Davies state, but I'll just call it the de Sitter invariant state, psi ds. It has the property that correlation functions in this state are thermal at the de Sitter temperature. The de Sitter temperature is 1 over beta ds, where beta is the circumference of the sphere. Remember, at fixed time, de Sitter space is a sphere, and beta is its circumference. When we assert that correlation functions are thermal, that means, for example, that two-point functions have two key properties. Analogous statements hold for n-point functions, but for brevity, I will only state these properties for the two-point functions. One is simply the statement that of time translation symmetry. The static patch is invariant under time translations. So if you shift both tau and tau prime by a constant s, that's a symmetry of the two-point function in the state psi ds. That's just time translation symmetry. But there's a much more special statement in the case of de Sitter space, which is the KMS condition. And the KMS condition says that you can reverse the order of two operators if you shift one of them in imaginary time by minus I beta. The origin of the KMS condition is that in Euclidean signature, de Sitter space is a sphere. And the orbit of the observer in Euclidean space is a sphere of circumference beta. And that leads to periodicity in imaginary time, which is the hallmark of thermal correlations. So the de Sitter correlations are thermal because of, roughly because of periodicity in imaginary time. And the precise statement of that periodicity for observations along the world line is this one. So a very precise statement of the KMS condition involves holomorphy of the correlation function in a strip in the complex plane with the two operator orderings, A before B or B before A, representing boundary values on the opposite sides of the strip. Now, including gravity in the observer, we define a special state in which the observer energy has a thermal distribution of the de Sitter temperature. So to give I take the observer wave function as a function of q to be e to the minus beta times q over 2. So its square, which is the probability distribution, is e to the minus beta q. So that's a thermal distribution of the observer energy. I include a normalizing factor. So this is a normalized state. And this times the natural de Sitter invariant state without the observer is the state that I'll call psi max. And in a few minutes, I'll explain the reason for the name psi max. So having included gravity in the observer, we replace operators phi of tau by gravitationally dressed versions of themselves, phi hat s, which is pi, with the same thing. Well, sorry. Remember, we have to replace the proper time tau by p, which is, if you like, the time measured on the observer's clock, except that you can shift it by an arbitrary constant s. and you have to project before and after onto positive Q. So these are well-defined operators in the observer algebra. And then there's one more generator of the observer algebra, which is Q itself. Then a straightforward computation shows the following. Remember, without gravity, we had two properties that express the thermal nature of correlation functions. So now I'm going to tell you what's the analog of those properties in the presence of gravity. The first is we still have time translation symmetry, but it acts on this parameter S, shifting S by a constant. So that property is obvious. What's much less obvious and much deeper is that the KMS condition simplifies. In the absence of gravity, the KMS condition involved a shift by minus I beta. In the presence of gravity, there's no shift. The KMS condition is simply replaced by the statement that reversing the order of the operators leaves the correlator unchanged. So in the absence of gravity, we had the standard KMS condition, which had to do with periodicity and imaginary time. It doesn't say that the two operators can be treated as commuting. If you reverse the order, you have to shift the time by minus I beta. In the presence of gravity, you can simply reverse the order of multiplication of the two operators. I'm going to check the chat again, if I can. Okay. Okay. One question is, why are only constant shifts in tau considered? The answer is that when I say that the observer Hamiltonian is mc squared plus q, non-constant shifts in tau aren't symmetries of that Hamiltonian. The observer Hamiltonian, if I say the observer has a mass m, that means that if a proper time tau is elapsed, the phase changes by m times tau. So the elapsed proper time is measurable. More general shifts are not symmetries. Maybe a way of saying it that you'd be happier with is that once I introduce the observer, there's a natural partial gauge fixing of all symmetries of the world line except constant shifts. And I've implicitly done that without telling it to you explicitly. Other question is, why can't we define any other operator instead of phi sub s? Well, phi sub s and q are the operators that commute with the constraints. So we have the gravitational constraint, which is the bulk constraint, and the sum of that plus q. And the algebra of all, I haven't stated this carefully as a precise theorem, but there is a theorem that the algebra of operators that commute with the constraint are generated by the phi sub s together with q. So now the simplified KMS condition with no shift in the time tells us that if for any observer A, we define the trace of A to be its expectation value in the state psi max, then the function that I've called trace does have the algebraic property of a trace. The trace of AB is equal to the trace of BA for any A and B in the algebra because of this condition 2 prime. So this function has the property that the trace of A dagger A is positive for all non-zero A, which means in particular that it's non-degenerate. So in other words, for every A, there's a B such that the trace of AB is non-negative. Well, not zero in particular, but actually non-negative. Namely, I can just take B to be A dagger. If this de Sitter state psi ds was normalized, then psi max is also normalized because I included a normalization factor, the square root of beta. And that means that the trace of the identity is 1 by this definition. Now let HDS be the Hilbert space we get by quantizing fields in de Sitter space in perturbation theory. It's important to understand what it describes and what it doesn't describe. States in HDS can have any number of graviton excitations, but not a number of them of order 1 over h bar. An h bar independent number of graviton excitations produces a back reaction on the geometry that's of order h bar, or in other words, of order g. So HDS doesn't describe states with an order 1 change in the geometry, only an order g change. So if we had a better theory, we would describe states with a bigger change in the geometry, but in perturbation theory around de Sitter space, we can describe states with an order 1 change in the geometry. Now let psi be any state in the de Sitter Hilbert space, and consider the function that takes a to its excitation value in psi. Roughly, but here I want the de Sitter Hilbert space tensored with the Hilbert space of the observer. So this is any state of the bulk fields together with the observer. Roughly speaking, because the observer algebra has a non-degenerate trace, you can hope that there's a density matrix in the observer algebra such that the excitation value of A in the state psi would be the trace of A times the density matrix. In other words, once you have a trace, you can hope to introduce density matrices as in ordinary quantum mechanics. Rather, as in ordinary quantum mechanics, we would expect rho to be a positive element of the algebra with trace 1. So, for example, let's find the density matrix of the state psi max. After we do that, we'll see how to describe the density matrix of more or less any state. The definition of the trace makes it clear that the density matrix of the state psi max is 1. Well, why is that? Well, by definition, the density matrix should be an operator sigma max with the property that the expectation value of A in the state psi max should be the trace of A times sigma max. But the definition of the trace of A times sigma max is that it's the expectation value of A times sigma max in the state psi max. So to find the density matrix sigma max, we must find the operator sigma max such that this quantity on the right-hand side is equal to this quantity on the left-hand side. And as you can see, the answer is that sigma max should be 1. So the state psi max has a density matrix of 1. That means that psi max is maximally mixed. It's analogous to a maximally mixed state in ordinary quantum mechanics whose density matrix is a multiple of the identity. In ordinary quantum mechanics, we usually have a multiple of the identity. Here we actually have the identity. The reason is that in this context, we defined the trace so that the trace of the identity is 1. Well, in ordinary quantum mechanics, one usually defines the trace so that the trace of the identity is the dimension of the Hilbert space. So because of that different normalization of the trace, here sigma max is 1, while in ordinary quantum mechanics, a maximally mixed state would have the density matrix that's a multiple of 1. So we found the density matrix of one state, namely the state psi max. Now, if A is any operator, consider the state that I'll call psi sub A, obtained by acting on psi max with A. It has a density matrix, and I claim its density matrix is just A dagger, because for any B in the observer algebra, the expectation value of B in the state psi A, using the definition of psi A, is the expectation value in the state psi max of A dagger BA, but that's the trace of A dagger BA. And using the cyclic property of the trace, which was property 2 prime, that's the same as the trace of BA A dagger. And this is the relationship that shows us that the density matrix of the state psi A is A dagger. So we found a density matrix of the state psi A obtained by acting on psi max with the operator A. But states psi A are dense in the Hilbert space, roughly by the Riesz-Leiter theorem, which is the fundamental result about entanglement in quantum field theory. So a dense set of states have density matrices. If we want all states to have density matrices, we need to take a useful further step. The Hilbert space HDS is the closure of a dense set of states of the form A times IDS. This is the closure in the Hilbert space sense. So inner products of these states are well defined, but states of that kind are only dense. The closure means you include limits of Cauchy sequences of such states. If we want every state in the Hilbert space to have a density matrix, we have to similarly take a closure of the observer algebra. The observer algebra, as I defined it, wasn't, until this point, it wasn't an algebra of Hilbert space operators. It was an operator product algebra. At this point, we do two things. Well, we define the closure as the von Neumann algebra generated by bounded operators in the observer algebra. Concretely, that involves doing two things. One, you set to zero, well, one, you include limits of operators in the observer algebra, but two, you also set to zero linear combinations of such limits that vanish as operators on this Hilbert space. So on the observer algebra, you have very few relations, only the universal operator product relations. But as Hilbert space operators, in a particular spacetime, there are a lot more relations. So to define an algebra adapted to the spacetime, you impose relations for that spacetime, but you also take limits. When you do that, you get a von Neumann algebra of operators on this particular Hilbert space. I'll call that closure A observer ds. So it's the observer algebra for the particular space-time de Sitter space. And it differs from the abstract algebra A observer by by taking limits that only make sense in de Sitter space, but also by imposing relations that only make sense in de Sitter space. Every state in this Hilbert space has a density matrix in this von Neumann algebra, technically affiliated to the von Neumann algebra. It's in this step that von Neumann algebras enter the picture. So until this page, we had an operator product algebra. Now we can talk about von Neumann algebras. I'm checking the chat, but I'm not seeing more questions there, I don't think. Oh. Well, I was asked if the projection onto non-negative Q caused problems. No, because the projection operator was a unitary operator. All statements I've made about operators are actually mathematically rigorous. And somebody asked me, how can a density matrix be a non-constant multiple of the identity? Well, in a two-dimensional Hilbert space, the identity has trace 2. And since the density matrix is supposed to have trace 1, in ordinary quantum mechanics in a two-dimensional Hilbert space, the density matrix of the maximum mixed state is 1/2 rather than 1, with the standard definition of the trace. If you normalize the trace so that the trace of the identity is 1, then you would say that the density matrix of the maximum mixed state is 1. Now, once we know that every state has a density matrix, we can define entropies as well. The von Neumann entropy of a density matrix rho is, as usual, minus the trace of rho log rho. In ordinary quantum mechanics, a maximally mixed state has a density matrix that's a multiple of the identity, and it has the maximum possible von Neumann entropy. The analog here is psi max with density matrix 1. It's clear that the entropy of psi max is 0 because the log of 1 is 0. And by imitating an argument that in ordinary quantum mechanics proves that a maximally mixed state has maximum possible entropy, one can prove that every other density matrix has strictly smaller entropy, in this case negative entropy. One way to make the proof is as follows. Let ρ be any other density matrix. Then for 0 less than t less than 1 minus t plus t times ρ, which I'll call ρt, is also a density matrix. A density matrix is simply a positive operator whose trace is 1. So if you take the linear combination of two density matrices, in this case 1 and ρ, with non-negative coefficients, you get another density matrix. Sorry, non-negative coefficients that add up to 1, then you get a density matrix. Let f of t be the entropy of ρt, which is minus the trace of ρt log ρt. So S of ρ is f of 1. Then f prime of, well, f of 0 is 0, though I didn't write it, because at t equals 0, ρ is 1. And f prime of 0 is 0, and f double prime of 0 is negative. The first statement is almost immediate, and I've written a proof of the second, though it might be hard to follow it on the fly. You use this identity for the logarithm of an operator, and that lets you calculate, once you have that identity, you can calculate f double prime of t, and you find after a little while that it's negative. And since f of 0 is 0, f prime of 0 is 0, and f double prime is negative, you learn that f of 1 is negative. So S is negative for any density matrix other than 1. Thus, the system consisting of an observer in a static patch in de Sitter space has a state of maximum entropy. The state consists of empty de Sitter space with the observer in equilibrium with the ambient spacetime. So with the thermal distribution of the observer energy. So long ago in the 1970s, Gibbons and Hawking suggested that there should be a notion of entropy for an observer in de Sitter space. They suggested it on the grounds that the observer experiences a future horizon. And Bekenstein and Hawking had associated an entropy to a black hole horizon. So Gibbons and Hawking said there should be an entropy for a de Sitter horizon, for a cosmological horizon as well. And they proposed that, in fact, the area of the horizon was the entropy. However, there wasn't a natural microscopic definition of entropy. Here, we sort of have a natural microscopic definition of entropy, only there was a renormalization involved. Because the function that we called the trace wasn't actually defined by counting states in Hilbert space. It was an abstractly defined trace. We defined a trace with the trace of the identity is 1, but if we tried to define the trace of the identity by counting states in the Hilbert space, it would have been infinite. So we really made an infinite subtraction, a multiplicative renormalization in defining the trace, but that corresponds to an additive renormalization in defining the entropy. So here we have a good microscopic definition of entropy, except that an additive constant was subtracted to make the entropy of the de Sitter horizon, to make the entropy of empty de Sitter space 0. But sub modulo that overall subtraction, we do have a natural microscopic definition of entropy in terms of the entropy of a state of an algebra. Why did it turn out that empty de Sitter space had maximum entropy? Well, the original argument that empty de Sitter space has maximum entropy goes back to Busso 25 years ago, who argued that this must be true based only on the second law of thermodynamics, because the static patch is empty in the far future. So, okay, Busso did not explicitly include the observer. So when we look at this picture, forget about the fact that I've labeled the left edge as the observer world line, but do think of this as the Penrose diagram of a static patch. With probability 1, any particle in the static patch is not precisely aimed in this direction and will cross the future horizon eventually and leave the static patch. So with probability 1, from Busso's point of view, the static patch is empty in the far future. But Busso said, therefore, the static patch spontaneously evolves to be empty. But the second law says that the spontaneous evolution of any system is toward maximum entropy. So he interpreted spontaneous evolution toward emptiness to mean that empty de Sitter space has maximum entropy. And so this argument that empty de Sitter space has maximum entropy was based purely on thermodynamic grounds with no microscopic definition of entropy. Now, in our context, we've defined the static patch by the presence of the observer. So by definition, the observer doesn't leave the static patch even in the far future. But the static patch will otherwise become empty in the far future. So in the far future, the static patch will be empty except for the presence of the observer. And the observer in the far future will be in thermal equilibrium with the bulk quantum fields. So Busso's argument adapted to the situation we are considering today with an observer present would say that the maximum entropy state would be what we've called psi max. So what we've done is to give a microscopic definition of entropy from which we can recover what was originally predicted purely on thermodynamic grounds. Now, in a more general spacetime, we have the observer algebra, but I don't know an equally explicit way to define the entropy of a state of the observer algebra. However, there's a fairly reasonable conjecture, which was inspired by Aaron Wall's proof of the generalized second law, and has some support from recent work by Chen and Pennington. The idea is to interpret the Hartle-Hawking no-boundary state as a sort of universal state of maximum entropy, generalizing empty de Sitter space, which has maximum entropy among states in a particular de Sitter spacetime. The expectation value in the no-boundary state, assuming the no-boundary state makes sense, the expectation value in the no-boundary state is a state of the observer algebra. I'll denote it as sigma of A. Then if A going to rho of A is any state of the observer algebra, then I would suggest that the relative entropy between rho and sigma for the observer algebra gives up to sign a definition of the entropy of the state seen by the observer. So this is a candidate for what would be meant in general by the entropy of a state of the observer algebra, where sigma is the no-boundary state. And in this formula, the most interesting version of this formula, we interpret the no-boundary state as being the state that comes from the gravitational path integral, as Hartle-Hawking actually said, with no attempt to normalize it. So relative entropy between a normalized state rho, see, rho should be a normalized state because we want to use it to define probabilities. But sigma we just take from the gravitational path integral. Relative entropy between a normalized state and any state is well defined. And this would be a definition of the observer entropy, which involved no renormalization, actually. So this would be a candidate for an absolute definition of the entropy of a state of the observer algebra for the observer in any spacetime. The only trouble is I don't know if that definition is correct. I don't even know if it makes sense, because our knowledge of the no-boundary state is so primitive that I'm not sure to what extent this concept makes sense. But anyway, this is what I would offer as a general definition of entropy. A lot of things are missing. So for example, what about an observer or a civilization that did not always exist? In this presentation, I used a field theory language. Can the discussion be generalized to string/M theory? Though the definitions make sense regardless, I want to remark that what I've said is most natural for an observer who, because of black hole or cosmological horizons, cannot see the whole universe. And of course, because we don't understand much about the no boundary state, we don't know if the conjecture I stated at the end is correct. At any rate, this is what I have to offer today. Thank you for your attention and for the invitation.
Thanks a lot so much. Thank you so much, Professor Witten. We have, I believe, one pending query in the chat. Should I take it up?
Let me look at it. I didn't see it.
Yeah, it's the one right at the end. It says the question is, would a background independent algebra for observers in the de Sitter with an initial Big Bang singularity be any different, or even any singularity resolved initial state?
Well, as I said, I don't understand how to adapt the discussion to a civilization that didn't always exist. So naively, it was crucial to get something interesting. It was crucial to have this constraint that shifted the proper time by constant. And you see, naively, if you have a Big Bang, you can measure the proper time since the Big Bang. So our universe is 13.6 billion years old or whatever. So naively, we don't have this constraint. To do something similar, I think intuitively, you'd like to say that when we make our observations, we aren't really able to anchor it in the absolute time since the Big Bang. And effectively, we have locally, we have this arbitrary shift in tau. I don't know a good way to say that. I haven't said anything. I haven't attempted to write anything in answer to this question because I haven't been able to say something that I thought was interesting and satisfying. But it's a good question. I recommend it.
Okay, I think I don't see any other pending queries to the best of what I can see. So I think that brings us to the end of this lovely lecture by Professor Ed Witten. And thank you so much on behalf of the organizing committee and all the folks online here on YouTube Live. So this is, as we all know, this is live on YouTube, and the recordings are going to be available on the meeting website. So thank you so much, Professor Witten. Once again, it's been, thank you. Thanks a lot.
Thank you. Thanks again for the invitation, and good luck to all. Be well.
Thank you. You too. Stay safe. All right, so folks, that brings us to the end of this two-day journey into the celebration of Professor Ashok Nath Mitra. I pray that this journey continues in the future, and we would just merely take a pause. Once again, my endless gratitude to, as I call my actually, earlier installments, I used to refer to them as the Packers, the Physics and Astronomy Club folks. Now I prefer to call them the Vanar Sena. So I hope they would excuse me. And I have, as I said, I've hijacked them for about 2 days now. And they're still sitting here in my office. I think this entire, the website, everything, I mean, all updates is all taken care of by them. So I think with that, I would like to request Gargi Didi to end this two-day journey with some sort of blessings, I guess, from our dearest Professor Ashok Mitra, as being the only living representative of the of the family, I guess. So I would very humbly request Dr. Gargi Mitra to please end this meeting for all of us. Yeah, okay, I need to unmute, yeah. So maybe I can take care, now I can remove that. So we can unmute ourselves and we can share screen. So yeah, Didi, please go ahead. Oh.
I'm so grateful for, I mean, everything, and especially to the boys who've been taking care of all the editing work and the website. I just don't know how to say thank you to them. The only thing I would have wished today was having yesterday to have Professor Basi Haider and somebody to take care of the Aligarh part of Baba's career. But I have some, I think, photographs, but then I'm just totally overwhelmed by everyone. It started so simply. I had just asked a simple question to Professor Sharma, Professor Satyendra Sharma, Satyendra Da, who had just called me once in September, and he immediately, I just said, could we have a WhatsApp group to just remember Baba on his birthday and his departure day. And while I was speaking, he was preparing a WhatsApp group. And then from that, it has snowballed into this awesome meeting. Professor Haridas joining, Professor Dr. Professor Kulshishta, Professor Patrick Da, so many, I mean, one by one, Indranil, Professor Majumdar. I can't just go. It's a long list, and then everybody started adding, and it just and snowballed, and then finally you, Alok. I just don't know how to say. I'm just overwhelmed. I don't even know. It's the way you've done everything. I'm just so grateful. I'm just so grateful. I'm sure I'm missing out names. Please forgive me if I've missed out any names. But Uncle Panchapakishan, of course, he was the soul of this, and all through. And I was so happy to have Professor Bhasin today. I was scared that he wouldn't be able to. I'm a bit disappointed that Professor Sudhendu Rai Chaudhary couldn't make it. I know that he was even trying to prepare a talk. And I think some other names also, they wanted to come. Especially, I'm disappointed that Professor Ramanathan, Dr. Ramanathan couldn't make it. He would have been really so, I'm really happy, of course, that Shashank, Professor Bhatnagar could take on that slot. And we missed also Professor Sami today. But anyway, whatever. So grateful for everything, Alok, especially to you. I have no words. You're the one who steered everybody. So God bless you.
Okay, so a final namaskar to everybody. Thank you. Stay safe, stay well. See you the other side of 25. Bye-bye. So we're ending the meeting for all. Namaskar.
Thank you, Professor Alok. I requested a reference from you. I just given the mail. Yeah.
I'll get back to you. I'll get back to you on that.
Yeah. So kind of you. Thank you. I'm sorry for the delayed reaction.
No. Please, yeah. Okay.
And especially, all the Professor Sinha, Professor Rai Chaudhary. Yesterday he spoke about things that I was so surprised to hear. I was looking for that information, that I knew that Baba had taken care of a scholarship. This is something that I'm concerned about. So for his father, he had done, but there is a lot of work to do for me. So lots of love.
Alok, I would like to express very, very special thanks for the very kind motivation by Professor Panchapakishan, who motivated us through his very first A.N. Mitra Memorial Lecture in the recent past. And that has actually become a kind of a driving force for many of us, or all of us.
Absolutely.
So he's always very inspiring. His words are very, very inspiring. So I
just want to add my one paisa bit on this. I just want to remind
I have my special pronouns to Professor Panchapakishan.
Absolutely.
So Professor Panchapakishan's lecture is available on the website. We have a link to that. So please, in case we have missed it, please do view it. Okay, a definitive and a conclusive namaskar, and I'm ending the meeting now. Okay.
Thank you. Bye-bye.
Thank you. Thank you.